Okay.
So next speaker is Romain Vasseur, who will talk about thermalization, integrability, and
Right. Yeah. All right, so let me start by thanking the organizers for putting together this conference and for inviting me here. So today I'm going to talk about some of my recent work in the field of many-body localization, and some more precisely I'll try to talk about those topics here of thermalization, integrability, and localization. And so before I start, let me thank my collaborators, Andrew Potter at UC Berkeley, Sid Parameswaran at UC Irvine, and Joel Moore at Berkeley, who's also here for this conference and who gave a talk earlier today. And if you're interested, pretty much everything that I'm going to talk about is contained in those 3 papers. All right, so my talk is going to be a bit different from most talks in that conference, in that I'm actually not going to talk, strictly speaking, about integrable systems. So since this is a conference on integrability, I figured I should kind of justify a bit why it's relevant to talk about many-body localization, or why I hope it's relevant to talk about many-body localization. So I think actually many-body localization is related to many topics that I hope will be of interest to some of you or many of you. And those topics at least strongly overlap with the main themes of that conference and of that whole program. So in particular, you can argue that entanglement plays a crucial role in the field of many-body localization, and I'm sure we're going to hear a lot about entanglement and entanglement entropy in this conference and program. Many-body localization is all about non-equilibrium dynamics. The relevant experimental systems are almost isolated quantum systems, such as cold atoms and things in optical lattices. And so there's many questions related to thermalization, dynamical phase transitions. And so once again, I think we'll hear a lot about all those topics during that conference. And lastly, I could also cheat a bit and tell you that many-body localized systems are in some sense integrable. There's at least a sense in which they are integrable. They're definitely not integrable in the usual Young-Baxter beta sense, but so I'll come back to that. There's some notion, and people often said that there's some sort of integrability in many-body localized system that's actually generic. And so also, of course, one of my motivations is that this field of many-body localization has attracted a lot of attention recently, so I figured I could at least try to convince you that this is an exciting and interesting field and tell you what some of the exciting questions are. All right, so here's the outline for the rest of my talk. So I'll have a rather long introduction, which will be a kind of overview of many-body localization in this context of integrability. So I'll try to tell you what many-body localization is, why, at least in my opinion, it's interesting and exciting, and what are some of the important aspects of it, and how you can probe it in some aspects of the dynamics in the many-body localized regime. And this will relate to this paper with Sid and Joel. And then in the second part of my talk, I'll tell you about something that's more of my main interest in that field. There's something that people now call excited state phase transitions, that are really new types of phase transitions that can arise in the presence of many-body localization, and that arise in excited states and not in ground states, so you can think of them really as dynamical phase transitions. And so I'll come back to those, and I'll describe some effective renormalization group type approaches that you can introduce to try to understand the scaling behavior of those excited state phase transitions. But so I'll come back to that in the second part of this talk. All right, so let me start by just telling you about many-body localization in general, just tell you what it is, why it's interesting. And so my starting point will be, I guess, the same starting point as almost all talks in that conference, just to think of the general question of thermalization, maybe in isolated quantum systems. Think of some isolated quantum system, perform a global quench on it, we inject some extensive amount of energy into it, and then we just time evolve, just pure unitary evolution of the Schrödinger equation, and wonder what happens if you wait long enough. Okay, and the related questions were being: is there some emergence of stat mech? Is there some notion of ergodicity? Can the system act as its own heat bath? Maybe if we look at some local observables. And so the generic expectation, at least, should be just the scenario of thermalization, right? So we know that statistical mechanics works. It's all around us. So somehow, if we just do this and perform this global quench, and if we wait long enough, we should somehow recover statistical mechanics, at least for generic systems. So that would be a natural expectation. So that's the scenario of thermalization. And you should go back to thermal equilibrium. So the way this happens, of course, for isolated quantum systems is kind of non-trivial, but understood in this eigenstate thermalization scenario. So roughly speaking, you can think of just systems in that thermalizing class are just acting as their own heat bath, that if you look at some small subsystem A, the rest of the system is kind of exchanging energy. If you wait long enough, you'll have statistical mechanics. So more precisely, what this eigenstate thermalization hypothesis is telling you is that the expectation value of local observables will be a smooth function over the spectrum and will coincide with prediction of, say, the microcanonical ensemble. And so to me, one property of one consequence of this ETH scenario will be that if you just prepare the system in some eigenstate, so time evolution is trivial, if you look at the reduced density matrix of a small subsystem A, even though the full system is in a pure state and is, like I said, not evolving, there's nothing happening, but if you trace over the rest of the system, so A bar, this will effectively take some Gibbs form, right? And with some effective temperature 1/beta that depends only on the energy density of the eigenstate you choose. So it doesn't matter which eigenstate you pick in some small energy window, they will also give you the same kind of, the same Gibbs density matrix. All right, so that's ETH, as of course I'm sure all of you know. So the only reason I'm quoting this here is that one consequence of ETH that I'm going to be using a lot in the rest of this talk is that if you take the entanglement entropy in that eigenstate, so the von Neumann entropy of that reduced density matrix, so here if ETH is true, this entanglement entropy should coincide with just a thermal entropy. So in particular, it should be extensive, which means that you should have volume law entanglement, which is of course what you expect traditionally for just generic quantum systems. If you take highly excited states, you expect them to have volume law scaling of the entanglement entropy. All right. So in this talk, I'm going to be interested in situations where this thermalization or ETH scenario is actually failing. Okay. And so we know, of course, that ETH is not a theorem. It's not something you can prove. It can definitely fail. And so one way it can fail, of course, is if you have integrability and you have this infinite set of extensive coarse quantities that strongly constrain the dynamics, in which case you have generalized Gibbs ensembles and so on, and things that will be discussed in this workshop. So one important point, of course, is that integrable systems are, from the point of view of thermalization, non-generic. Okay, if you add some perturbation to some generic perturbation to an integrable systems, you'll break integrability in general, and you expect you'll go back to thermalization. So you might have some interesting crossover dynamics, you might have some interesting pre-thermalization, but eventually, if you just take a generic system, you should thermalize. All right. So another way you could think of escaping thermalization is to use localization. And going back to Anderson localized systems and what Anderson taught us more than 60 years ago now. And if you just take some non-interacting particles and you crank up disorder enough, you could localize all the single particle wave functions. And so more precisely, if you think of just a one-dimensional system, so I'm going to be thinking mostly, actually only about one-dimensional systems in that talk. So if you think of, say, just non-interacting fermions hopping in some potential spinless fermions, just put some random chemical potential, we know that any amount of disorder is actually enough to localize all the single particle wave functions at all energy, so they will have exponential tails instead of being extended. And so this phenomenon of Anderson localization has been now observed experimentally in many systems, and here I'm showing those beautiful cold atom experiments from the aspect group, where you can really see this exponential tails. So such Anderson insulating systems fail to thermalize, they don't satisfy ETH, and so just the physical intuition that you might have is that the excitations that would usually move around and transport energy and make the system act as its own heat bath are here localized by disorder, and so you don't have ETH, you don't thermalize. So one more technical way to see this is just to compute the entanglement entropy in excited states, and if you take an excited state of an Anderson insulator, so if you take an eigenstate of this Hamiltonian with disorder, you can quite easily argue that the entanglement entropy will be basically order of the localization length, take an interval of size L. So it won't scale with the size of the interval. So it won't be volume law entanglement, it will be area law entanglement in all excited states, in all eigenstates. And so you can see here that ETH is violated. All right, so at this point you could just probably argue that I'm cheating a bit because this is also just an integrable system. It's actually non-interacting, right? So there's no, okay, this is still non-interacting and non-generic. And it's just not surprising that it doesn't really thermalize. So this is where many-body localization comes in. So it turns out that whereas integrable systems are non-generic, this phenomenon of localization is, and can persist if you add weak to moderate interactions, if you have strong enough disorder. There's some notion in which this localization phenomenon persists in excited states. So let me be precise here. I don't want to think at all about ground states. So people thought about localization at 0 temperature and in ground states. It's not what I want to think about. I want to think about finite energy density, global quenches. And so there's some notion in which this localization phenomenon persists into excited states at finite energy density when you add interactions. And in particular, that ILO stable turns out actually to be stable. So you'll have this ILO scaling in excited states even at finite energy density. So let me kind of be just more precise and summarize a bit. So for this question of thermalization in isolated quantum system, there's only 2 generic scenarios that we know of, at least as of now. So the first one is just this scenario of thermalization of ETH. And basically you just forget about your initial condition. So of course, okay, you have unitary dynamics, so you don't forget anything, you don't lose any information, but your memory of your initial condition is kind of hidden in global degrees of freedom that you cannot access when you look at physical local observables. And so you essentially forget about your initial condition, and this allows you to have a statistical mechanics description in terms of a reduced number of parameters like temperature, chemical potential, one per extensive quantity that you might have in your system. In such thermalizing system, excited eigenstates are highly entangled. That's what I said, and you expect also typically rapid spreading of quantum information and conserved quantities. So you also typically expect diffusion or diffusive transport in such thermalizing systems. So I'm going to be referring to those thermalizing systems as the classical equilibrium world. Equilibrium because you do thermalize, and classical because I'm going to be thinking of isolated quantum systems that's at very high energy density. So that if they do thermalize, they will do so at very high effective temperature, and they will behave effectively classically. Okay. And so on the other side of the spectrum, the only other generic scenario that we know of is actually many-body localization, which is the complete breakdown of this thermalization picture, and which is, like I said, generic. So if you take a many-body localized system, you add some generic perturbation, weak perturbation, it will remain many-body localized. So it's really like a phase. And so those many-body localized systems, if you want, remain very quantum, even at very high energy density, even if you think of highly excited states, think really in the middle of the spectrum. And there's some local quantum information that persists to infinite time. So if you want, you always remember about your initial state. You never forget about your initial condition. And I'll tell you just in a few slides why you can think of this as being related to some kind of integrability. One important properties of many-body localized systems is that excited eigenstates have low entanglement. So whereas there you had highly entangled volume law entanglement in excited states, in a many-body localized system, excited eigenstates have area law entanglement. So if you want, they look like gapped ground states. This is actually a very surprising point. At least it was very surprising to me. So usually we always argue that ground states sit in that very small corner of the Hilbert space when you have low entanglement, whereas typical states in some Hilbert space have a volume law entanglement, highly entangled. And that's why numerical methods like DMRG work so well, because they target states in that small corner of the Hilbert space. So here in many-body localized system, actually all excited states live in that very small corner of the Hilbert space. And this is actually generic. And at least to me, it was very surprising when I heard about this at first. Right?
But this is, we've been saying that the only parameter for the many-body localization is the area law.
Well, so I don't know if you want to call this another parameter, but yeah, that's the way people check it numerically. See this you can look at various things. You can look at level statistics. So here you expect, GOE kind of level statistics, and here you have Poisson, like in integrable systems actually. So there's many things you can look at to investigate this, say numerically, and one way is to look at entanglement entropy. So you can.
Why do you expect Equation statistique for the...
Because the levels don't know about each other, basically. So there's no level repulsion. And yeah, finally, there's no energy transport, hence localization, but that's by no means a definition. Okay. So this field of many-body localization, like I said, has attracted quite a bit of attention. So let me kind of tell you why some of the important points and some of the surprising aspects of many-body localization. So beyond this, MBL versus say ETH or scenarios of this really fundamental question of validity of statistical mechanics that I think is very interesting and quite fundamental. So the most interesting property, at least in my opinion, one of the most interesting properties is what I already mentioned, that highly excited states have area-low entanglement, so they quote-unquote look like ground states. So this gives you some intuition why you can actually have completely new phenomena in the presence of many-body localization, because now you can have phenomena that you thought would occur only in, say, zero-temperature ground states that will now occur in highly excited states. And if you want, you can think of this as being a consequence of this area law, or at least some intuition why this can be true. And so in the presence of many-body localization, you can have completely new phenomena. You can have things that are completely forbidden by statistical mechanics, usually. And it's okay because statistical mechanics doesn't apply to many-body localized systems. So for example, you can have ordering below the lower critical dimension. You can have some quantum coherence at high energy density. You can forget about all the Mermin-Wagner type arguments that will tell you that quantum order is destroyed by thermal fluctuations. You can have localization and disorder if you want protecting, even if that sounds counterintuitive. That was first argued in that paper. Protecting quantum order, so you can have symmetry breaking quantum order, you can have topological order, you can have symmetry protected topological order, all protected by localization if you want, at finite energy density. And so for example, you can have symmetry breaking order even in 1D at finite energy density, even if that's completely forbidden by statistical mechanics in the presence of localization. Okay. So I'll give more concrete examples in the second part of this talk, and which means that if you want, you have different flavors of many-body localized phases, so you have different type of quantum orders, which mean you have phase transitions between those, and which means we need tools to understand those phase transitions, and so that'll be the second part of my talk. And so finally, of course, one important motivation is to think about our recent ability to engineer almost perfectly isolated quantum system experimentally, and particularly in cold atom setup. And I just want to mention, so I'm not going to talk so much about experiments in that talk. I just want to mention that we've had at least two very recent experiments on many-body localization last year. One from the Block group on cold atoms. And so if you're interested, you should ask Ulrich Schneider, which I guess is not here yet, but should be around tomorrow. And one on trapped ions from the Monroe group. And so this, oh, he's okay. Oh, you're here. Okay, so you're not okay. I don't know if she's going to talk about this tomorrow. Okay, so you'll hear more about that tomorrow. All right. So, like I said, I'm not actually going to talk so much about experiments here, but we'll hear more tomorrow. All right. So I don't want to talk too much about this part here because it's not my work. But since this is a workshop on integrability, I thought I would mention and tell you why people often say that many-body localized systems are integrable. So so there's a so-called local integrability picture that emerged over the years. So originally it was more like a phenomenological description. Then it became more rigorous. There were some renormalization group type arguments. There was some numerics, and now there's actually perfectly mathematical proof, almost perfect mathematical proof by Imbri that this is correct, at least for the X-axis spin chain with random fields. So now there's a lot of evidence that this is true, that many-body localized systems are actually characterized by conserved quantities that are local, actually quasi-local. And so here I should just precise that I don't mean the same local as in integrable systems. So here I have conserved quantities that are not sum of local operators. Those guys that are called, so usually people call them localized bits, are new effective spins. So you can think of it as a Tauzi operator, as a new effective spins, which goes localized spins, which commutes with the Hamiltonian. So it's a conserved quantity, and it's local. So it's quasi-local. It has exponential tails. It's not a sum. So I here you can think as labeling a site. And you can find an extensive number of those guys. Hence the name integrability. You have an extensive set of conserved quantities that are local. So the important point here is that this integrability is actually generic. Okay. So if you take this system in the many-body localized phase, so the typical system that most people study is just XXZ with random fields. You can construct, at least iteratively, those conserved quantities. And if you add some generic perturbation and in disorder is strong enough, you can just change your definition and redefine those guys again.
So these commutational relations are true for each realization of the random phase?
Yeah. For one disorder realization, you can define those guys. Yes. Which is very surprising, right? So it's,
You mean they are true almost surely for each realization?
Yeah. There's some resonances, there's some notion, there are some subtleties hidden here. This is assuming that the full spectrum is localized, so here if this is true, really the full spectrum will be many-body localized. The more precise definition, almost all eigenstates are actually localized, so there are some subtleties, but yeah. But this is still a very surprising emergent type of integrability that is generic, and that occurs when you have many-body localization. And so you can write the effective Hamiltonian, if you want, of the many-body localized phase. So you can, or in other words, you can diagonalize your Hamiltonian and find some local unitary transformation that will diagonalize your system and put it in this form, expressed in terms of those conserved quantities. So since they commute with tau z, you can just, the general expression would be something like this. It looks very much like, if you want, almost a Fermi liquid type of Hamiltonian, except that it's in real space now. So if you want those tau z's, think of them as the generalization of just the occupation of the orbitals in a non-interacting case, right? So if you have a non-interacting Anderson insulator, that would be just the first term, which is just diagonalizing free fermion, and tau z is telling you if your orbital is occupied or not. And so they're local, but now you have interactions, and so you're not only quadratic and you have more terms. And since you localize, you can argue that those coefficients are actually decaying exponentially. So like I said, let me not spend too much time on this, but that's basically the picture that has emerged over the past few years on many-body localization, and you can understand many of the properties of many-body localized systems using that formalism. And so in particular, I just want to mention a few of the peculiar properties of the dynamics in many-body localization. So basically, if you think of just this picture, this is telling you that many-body localization is not that different from Anderson insulators in the sense that, like I said, those tau z's, you can really think of them as kind of generalization of occupation of, sorry.
I don't know if there's anything else, but so is it zero in the thermal limit, right? The commutational relations are true for a single realization of
there's zero, yeah.
No, but you have to take the thermal limit to be exactly zero, right?
Yeah. True. Yes. Right. Well, yeah, definitely. No, that's definitely right. Yeah, I was also thinking. Yeah. All right. So it turns out that the many-body localized phase itself has some interesting dynamics. In particular, it's characterized by some log growth of entanglement after a global quench. So the setup is kind of very simple. Let's imagine you take some, I wrote Heisenberg, but let's think of XXZ in random fields, right? And you start from some just initial state that's like a random SZ state. So zero entanglement, or just a nail state if you want. So this is a global quench, zero entanglement entropy initially, and then you time evolve and see what happens. So this was done in those numerical papers, and here I'm showing the data from this paper from the Berkeley group. And so if you have zero interaction, so if this is a random XX chain, if this is an XX chain, entanglement is growing, and then you have a plateau, basically. Okay, so, and this plateau is just order of the localization length. So entanglement is growing, and then you realize that you're localized, and this keeps going even if you're in the thermodynamic limit, so you just have this plateau. And if you look at transport, so this is some transport of conserved quantity, it basically does the same thing. So you transport, and then you realize you're localized, and you get stuck. And so the surprising thing, or at least surprising at the time, is that if you turn on interaction, so energy and particles are still localized, so you still have no transport, but entanglement is actually growing. So when you turn on interactions, you have this entanglement that keeps growing very slowly, actually logarithmically, and this entanglement grows forever, so it doesn't stop. If you have a thermodynamic limit, if you're in the thermodynamic limit, this keeps going forever, so you have this unbounded growth of entanglement.
how this fits with the picture before.
Yes, so I'll get back to this just in a sec. So initially this is actually how this picture emerged. So initially there was the numerics, and people were confused about this log growth of entanglement, and were thinking maybe this is a sign of slow equilibration, right? So people thought, at least initially, that if you localize, entanglement should also be bounded and stop at some point. So actually this is how this picture emerged. You can just, if you think of just this picture here, so eigenstates in this basis of Tarsis are of course trivial. I'm just have as the Ising state for this Tarsis, but the dynamics is actually not completely trivial. So in particular, if you just generate some superposition of spins up and down, say on one side I, and some superposition on side j, you can just convince yourself that this term here will create some dephasing and will actually contribute to entanglement growth. And the fact that it's growing logarithmically is just because those interactions are exponentially decaying. So you can make this more precise, but basically just starting from this, like I said, initially it was more of a toy model or some phenomenology. Now we know that it's really like actually a rigorous picture for this many-body localized phase. You can just convince yourself that this term and the higher order ones will generate entanglements or dephasing, and you can recover this log growth of entanglement from there. So like I said, historically, it's actually started by being numerics, and then people interpreted this and came up with this picture here.
Sorry?
Yeah.
When you show that toy model Hamiltonian, right?
Yeah.
Where you have this exponential decay,
yeah.
It's typically an envelope, not because these numbers are fluctuating.
You can argue that the typical value of those coefficients is exponentially decaying, and you can argue also that the probability of them being large is also exponentially decaying. So yeah. But yeah, the coefficients will depend on these other.
Yeah. But when these numbers are fluctuating, doesn't influence this log.
No, yeah, this is still, no, for typical disorder realization, this will be exponentially decaying. That's the only thing that matters. Yeah. So like I said, now this is not a toy model. We should really think that for xxz, there's a way to diagonalize your Hamiltonian and bring it in this form. So like, right, and just to conclude this section, let me just mention that this log t growth of entanglement is now, you should think of this as, if you want, really a fingerprint of the many-body localized phase. So you see things getting stuck, but you still have this log growth of entanglement. So there's been a lot of activity to actually find some ways to measure that log growth of entanglement experimentally in some way. And of course, you usually have the problem that measuring entanglement is hard. But as it turns out, actually, the physics of this slow log growth of entanglement is much simpler than just entanglement, actually. Right? It's just those terms here that dephase and that create that log growth of entanglement. And so there's been many proposals either to measure this log growth in some way using spin echo or quenches. And so with Joel and Sid, we've argued that, for example, you could look at the revival rate of local observables. And that would pretty much show up the same physics. So let me not go into the detail, but you can just think of coupling your system, many-body localized system, to some two-level system, say a qubit or some external spin. So if this is ergodic, then this will act as a bath for your spin, and okay, you won't have basically any revival, because in order to have a revival in your many-body wave function, you need to synchronize 2 to the L frequencies, if L is the size of your system. But now if you localized, this effective spin, since it's coupled locally to the system, sees effectively only of order of the localization length spins. And since you're non-interacting, let's imagine first you're non-interacting, sorry. If you're non-interacting, the spectrum is additive, so you only have order side of the system instead of 2 to the side of the system frequencies. So you see effectively just psi frequencies, 2 to the psi. So basically, if you have a non-Anderson insulating system, you'll see many revivals if you just look, for example, like magnetization. And when you turn on interactions, you will lose many of those revivals. But the way you lose them, since you're just coupled locally, is in the same way you'll generate this entanglement. It takes you time to realize that you have some spins and you have interactions. And you can argue that the revival rate is decreasing logarithmically, basically by exactly the same physics that gives you this entanglement growth. All right. Okay, so that's it for the kind of general long introduction to many-body localization. So now, in my remaining time, I'd like to tell you about the so-called excited state phase transitions that can arise in the presence of many-body localization, which is, at least in my opinion, really one of the most exciting things about MBL. All right, so let me just give you some kind of motivation of just some kind of preview of what I want to tell you. So basically what I want to argue is that in the presence of many-body localization, you can have some notion of, say, quantum criticality at quote-unquote infinite temperature, where by infinite temperature I mean really states in the middle of your many-body spectrum, or dynamics at very high energy density. So of course, when I tell you this, it probably sounds completely counterintuitive. So probably when you think of quantum criticality or just critical phenomena in general, you have in mind all those nice unifying concepts of modern physics, of renormalization groups, scaling law, universality, and you also probably have in mind that interesting universal things should happen only at low energy and low temperature, right? And so in particular, if you just think of some typical phase diagram with a quantum critical point separating two states, ordered and disordered, with maybe, say, so finite temperature phase transition and some critical fan, if you go to very high energy temperature and some high energy regime, you basically don't expect anything interesting to happen, right? So you would think that if you go to very high temperature, you should be essentially, say, classical, and so you should not have any quantum mechanics remaining if you go into this very high temperature regime, and there should be no universality left also if you go to high enough temperature. Okay, and that is, of course, usually true. But the crucial assumption that we're making here is that the system is at thermal equilibrium, and so it's characterized by some temperature T, either because it's coupled to some bath or because it's thermalizing and acting as its own heat bath. But here, in many-body localized systems, so you never go back to thermal equilibrium, so you never have this picture. And actually, you can have some interesting quantum universal phenomena occurring in this high-energy type regime. Okay, and you can have phase transitions, and you can have universality occurring in this at very high energy. And you should rethink basically all the tools we have to understand phase transitions, like the renormalization group and things like this, since you don't really have any notion of low energy anymore, but you still have some universality. And so this led to this notion of excited state phase transitions in many-body localized systems that are now phase transitions that occur not in ground states, not at zero temperature, but in highly excited states in the middle of the spectrum where you would usually think nothing interesting would happen, and eigenstate would be kind of almost random states. And so there's really two types of such phase transitions. So the first one is actually the phase transition between ETH, or this ergodic behavior, and many-body localization as a function of, say, disorder. So if you go back to this, say, XXZ chain with random fields, so you have fixed interactions. So let's even take Heisenberg. So interactions are fixed. So you know that if you put some weak enough disorder, so you break integrability, but you expect to be in some phase that should satisfy ETH, where statistical mechanics should work, you should have extensive entanglement, and usually your usual intuition should be okay. But now if you believe what I told you in the first part, if you crank up disorder enough, you should have a many-body localized phase, and where entanglement should scale in excited states as a constant, so area low entanglement, and where statistical mechanics fails. And so the obvious question is, what is going on at this point here? It seems that you have some critical value of the disorder when you have a phase transition, really that now occurs in highly excited states in the middle of the spectrum. So you can also think of it as a dynamical phase transition if you want. It's only something you would see using dynamics. But if you do, say, exact diagonalization, you would see things changing some properties of eigenstate that would change sharply from here to there. So here you would have volume low entanglement, and here you would have area low entanglement. And if you think about it, this is a completely new type of phase transition. There's no other phase transition that does this, that goes from an area low state to a volume low state. Okay. We're talking about property of highly excited states, and as of now, there's only two theories of that transition. One by myself, Andrew Potter, and Sid Parameswaran, and one by Ronen Vosk, David Hughes, and Ehud Altman. You can think of them as some effective renormalization group approaches. I might just say a few words near the end of my talk about them. If you're interested and you want details, you can just go and talk to me. I would be happy to tell you more about our ideas for that transition. And so the other type of excited state phase transitions you can have are between different many-body localized phases. So I already told you could have different flavors of many-body localized phases, and you can actually have phase transitions between them and represent criticality between MBL phases. Yeah.
How do you know that these are actual phase transitions or sharp transitions and not just crossovers?
Okay, so that's a really good question. I don't in principle. I have no. There's some numerical results. There are some, and we have some some analytic understandings of those transitions. Actually, I should maybe just have mentioned this for many-body localization. Most of our understanding of many-body localization comes from either physical intuition, small-scale numerics. There's a very few things we know for sure, right? So this integrability picture, like for XXZ chain, is probably one of the only rigorous results we have. Very little is known about those transitions. Everything that I'm going to tell you is kind of based on some, if you believe some renormalization group approaches, you'll see that they should be actual phase transitions. I believe they're actual phase transitions. Yeah, there's no theorem telling me that they should be. Yeah.
But I guess to check this first picture, the one that you have a crossover between the...
So yeah, that I guess should be an actual phase transition, right? If you believe in thermalization, then I think it should be some actual phase transition.
And then I think if you even take the Anderson model, you should see that. Because, I mean...
No, this is in, okay, I need interactions to have that transition, right? So that transition, so let's say in 1D would be localized all the way, right?
For every value of the disorder. Yes.
Yeah, so if you're 1D and you don't have interaction, you should have localization all the way, so nothing happens. I really need interactions to have that phase transition and seeing. Yeah.
What qualifies that line as being a line of critical point below?
Below?
Yeah, what is the critical?
Mm-hmm.
Already phase transitions, you don't know. I mean, yeah.
Okay, so I'm calling this a phase transition. Of course, I don't have thermodynamic. Okay, there's no phase, and it's generalizing. But I have two states, and actually, that's what I'm going to talk about for the rest of the talk. So let me just maybe iterate, and we can. I'm going to talk mostly about those. So, and so basically, just my main point is whether we can actually have new university classes far from equilibrium. Okay, and so when I talk about phase transition, obviously, I generalize the notion of phases to this many-body localized phase case. Okay, so just to be slightly more precise, so I told you that many-body localization can somehow protect quantum order, and just to give you a more concrete example, let's think of just a transverse field Ising model. 1D, so I just have a transverse field, and let me imagine I add interactions that just preserve the Z2 symmetry, weak interactions, but just make the system interacting and non-integrable. So if we have uniform coupling, we know that the phase diagram should be something like this. So we should have a quantum phase transition at 0 temperature, and we should have a paramagnetic phase, some phase that breaks the Z2 symmetry. And since we're in 1D, we know that if we go to finite temperature, we should have no true quantum order, and we should have no phase transition at finite temperature, right? So that's usual statistical mechanics. So now the amazing thing about many-body localization is actually if we take strongly random couplings, we actually have some transition that remains, that separating two different many-body localized phases, one which is quote-unquote a paramagnet, and one where you actually break the Z2 symmetry of the model in all excited states. Okay, so the Z2 symmetry of this Ising model is broken in excited states, so it's broken in some spin-glass manner in the sense that your states will have just domain walls of Bézier spins if you want, and so you can characterize it by some Edwards-Anderson type order parameter, but there is some broken symmetry in your excited state, in all eigenstates on that side, so there's really a transition in your excited states as a function of, say, this parameter here, if you take some randomness. And so the question is, what is that phase transition? Precisely your question. What can we say about this, and what kind of tools can we actually use? And so the tool that I'm going to be using is some generalization of the strong disorder renormalization group approach that has proven very useful to understand at least properties at 0 temperature. So here, those phase transitions are really strong disorder phase transitions. So they occur at very strong disorder. So both phases are many-body localized. So let me just remind you how this real space renormalization group approach works at 0 temperature. So that was done by all those gentlemen, and in particular by Fisher. In this example of, say, the Ising chain, so the idea is to assume you have very strong disorder, and you're just going to find the strongest coupling in your chain. And if you assume strong disorder, this largest coupling will be typically much larger than its neighbors. So to first approximation, you can just diagonalize this strong bond, ignore the rest of the chain, just diagonalize this strong bond, and put spins in their ground state. So for example, you can just take those two spins here, diagonalize, let's imagine the strongest coupling is some Ising term like that. The ground state is like aligned spins up, up, and down, down. So you can think of them as being a new effective spin if you want. And then you just take into account the rest of the chain perturbatively. And you can compute new effective couplings by just quantum fluctuations. So for example, here, you'll find that using second order perturbation theory, you'll find there's some effective transverse field acting on that effective spin, just given by this formula. And so you conserve the form of the Hamiltonian during that flow, so you can just keep going and identify the strongest bond, diagonalize it, and keep going like this. So this looks completely approximate, so you're using second order perturbation theory. It doesn't look exact at all, but it turns out it's actually a very remarkable fact about this approach is that it's actually so people call it asymptotically exact, which means that it actually leads to exact results for universal quantities like critical exponents. And so the reason is the effective disorder strength in your chain actually increases as you flow. So the more you run the RG, the more accurate you become. And so actually, it is widely believed that you get actually exact results with approaches like this. So this is all zero temperature physics. So here in this talk, I want to think about excited states. So we need to generalize this to think about excited states, or dynamics if you want. And so this is now known as RSRGX, where the X stands for excited states, which is basically a rather straightforward generalization of this, of this RSRG. So you still follow essentially the same procedure. You find the strongest coupling, but now instead of putting it in a ground state, you can put it in some excited manifold. So for example, if you find a strong Ising bond, you can also choose to, say, project this, do spins into this manifold where they aren't aligned, and kind of keep going like this and try to generate excited states. So it's convenient to represent the outcomes of this renormalization group in terms of some renormalization group tree when you have energy, and this is the number of renormalization group steps that you take. So in the ground state version, each step, you kind of find a strong bond, you diagonalize it, and you try to minimize the energy at each step. And if you want, you walk down that tree, and you always pick the lowest energy outcome. So now in this RSRGX version, at each time you find a strong bond, you make a choice, and it's kind of up to you what choice you make. And you can choose to increase the energy, go up, and maybe go down. And at the end, you end up with so there are many branches to that tree, and each branch is some excited state. Okay. And so in principle, you can use this method, say, just numerically to generate some good approximations of all your many-body excited states. Okay, so you can check numerically it works well if this order is strong enough, at least. And so here, for example, that would be for a finite size system, and you see like you have 2 to the L eigenstates there, and your eigenstates is like kind of taking one branch, particular branch in that tree. And so the scale that becomes small in that renormalization group are just energy gaps. So now you don't minimize the absolute energy, but there's some notion in which you resolve smaller and smaller energy gaps. So this RSRGX approach was first introduced in that paper by Pecker and collaborators in this example of the Ising model, precisely to actually argue that there were 2 phases and a phase transition in this Ising model. And they used some kind of Monte Carlo sampling of this renormalization tree. There's some related dynamical version by Vosk and Altman. And so with Drew and Sid, we basically argued that you can first generalize this to an infinite family of models. So you can either think of them as anionic chains, or maybe for that audience as RSOS chains. It doesn't really matter, it's just a way to generate infinitely many universality classes if you want. And more importantly, we actually argued you don't need to do some Monte Carlo sampling, you don't need to do numerics, you can actually write down analytic flow equations to understand properties of eigenstates in the middle of the spectrum. So you can actually write down analytic flow equations, get exact results, exact critical exponents from that real space RG for the properties of highly excited states. So the outcome is precisely, so this nature of those phase transitions is something that we call a quantum critical glass, which is, if you want, a critical version of many-body localization. And essentially, it's this strong disorder infinite randomness physics that now you find in excited states. So those quantum critical glasses are kind of characterized by the fact that excited eigenstates have now quantum critical properties. So just like I told you that in a many-body localized system, excited eigenstate will look like gap ground states, here along those phase transitions, actually, there can be actual critical phases. You have quantum critical excited states. So you have quantum critical properties in the middle of the spectrum at very high energy density. And in general, the critical exponents are different from zero temperature ones. So if you want to get new non-equilibrium universality classes with exact exponents, or at least exact exponent that you can compute using those strong disorder renormalization group approaches. And so those critical variants of MBL can be characterized by many properties. In particular, they have log L scaling of entanglement, which is kind of characteristic of just criticality in 1D. but now you find it in highly excited states. So you have excited state that with entanglement that scales at log L, which is still not thermal, so it doesn't satisfy ETH, but it's not many-body localization either, which would be ILO. So you get, if you want, this quantum critical version that is still localized in the sense that it doesn't satisfy ETH. They also have power law correlations, critical exponents, many things that you can compute exactly using the strong disorder or normalization group approaches. Yeah.
These are the value small states, right?
Sorry? Yeah.
They are value small states.
Oh, you mean, okay, random singlet. There's some notion of in which there are still random singlet type physics, yes, in those, yes. Yeah, it's basically this infinite randomness physics that you had for ground state that is not generalized and comes up in excited states.
With this renormalization group method, I thought you can study the case in which you have two competing disorders, right? You cannot study the competition between order and disorder. I understand correctly?
No, you can apply, for example, this was done for Ising model, for example. So.
Yeah, but you always have random couplings and random field, right?
Right, they're both random. I cannot study the MBL phase transition with it.
So you can study transition between two kinds of many-body localized states.
Yes, precisely. So all this, so those quantum critical excited states is only for the second type of phase transition that let me go back. So I had that picture with, so this is only for this type, not this one. Okay, so I can, here the claim is you have quantum critical excited states that you can capture with those strong disorder normalization group. So in the last, say, 5 minutes of this talk, I just want to say a few words about this even more interesting phase transition, which is even more intriguing in that there I cannot use a strong disorder normalization group to study. The phase transition that occurs between ETH and MBL serves a function of disorder if you have fixed interactions. So I already mentioned it's really a new kind of phase transition. There's no other phase transition that you can think of, at least that I know of, that will be between volume law and ILO entanglement. So the obvious question is, are there some universal scaling properties? Once again, very non-trivial because you think about high energy physics, essentially, and it's not obvious at all there should be anything universal in that regime. This is a very hard problem. You have interactions, you have disorder, and we're talking about something that's very non-equilibrium and very highly excited states. And so in particular, I cannot think of any field theory description of something like this. And if you thought maybe you could do numerics since 1D, the only numerics we have is basically limited to less than 20 spins for that transition because you need to do some full exact diagonalization. You need to compute all the excited states to understand that phase transition, so you cannot use like just DMRG or things like this. And so 20 spins is probably not enough to numerically understand that phase transition. So we need new approaches, and so the strong disorder RG method that I mentioned will actually fail that, if to describe that transition. So actually that transition will happen when that strong disorder normalization group fails or starts failing. So we need some novel or new renormalization group approaches, and that's what those two, at least those two papers are trying to take one step in that direction. And just like very briefly, because it's the last few minutes of my talk, I want just to mention this paper with Andrew and Sid. We basically have some effective model to try to understand that transition, where if you want, we have still some renormalization group type structure where we now try to iteratively merge some, let me call that ergodic hotspots or resonances that destroy many-body localization. So we start from the strong disorder regime, and we try to identify some regions that are, if you want, less localized. And we have some effective method to try to merge them and see if they percolate. So it becomes almost an effective percolation model where we try to merge those ergodic regions. So I'm not going to go into the details. If you're interested, you can go and talk to me. And so this gives some effective percolation model. So this is like the percolation probability of those ergodic regions. And so you can do some finite size scaling on some very large systems, and you can see that you seem to have some transition where here you don't percolate at strong disorder, where at weak disorder you do percolate, and where you percolate, you interpret this as a delocalization transition. So we can extract some scaling properties. So in particular, it seems that it has some second order type structure with some diverging correlation and some exponents. And the last thing I want to mention is that the ergodic phase is actually more interesting than we could have thought. So you would think maybe this ergodic region is kind of maybe not that interesting. It's very high energy density, and it will behave essentially classically. And probably if you do transport, you would expect state diffusion. So if you prepare a wave packet at time t=0, energy wave packet, look at the way it spreads, natural guess would be diffusion. And in fact, this is not what happens. And there's some interesting transport properties in that ergodic region. Instead, you get some anomalous subdiffusion that you can understand either from scaling argument, and we can also get it in our approach. And so the width of your wave packet scales as a power law with the time. So there's some subdiffusion. You go slower than diffusion, and you have some continuously evolving exponent z that you can think of as a dynamical exponent if you want. That is non-universal, but that diverges in some universal way near the transition. So you have some anomalously very slow transport, and we can argue from some scaling correlation that the exponent that controls this is actually the same as the correlation length exponent. So you see that you seem to have this, even though you have very high energy density in 1D, you seem to have this very rich universal structure with some continuously evolving exponents, some scaling correlations, and there's still a lot that we're learning about that transition, and this is kind of just a phase diagram that we have for that phase transition as a function of system size in disorder and various scaling regimes. All right, so just to conclude, I hope that I've convinced you that there are some, MBL provides you with some very interesting playground to think about basic questions of statistical mechanics, validity of statistical mechanics. I mentioned this very important property that you have some quantum coherence in hot matter, if you want, so in high energy density, and it leads you to new types of criticality. You have a whole new zoo of phases and phase transitions, and we need new theories to understand them. So I mentioned those quantum critical glasses, which are like phase transitions between MBL phases, where you have some quantum critical excited states. And I just said a few words about this MBL phase transition, and there's still a lot to be done to try to understand what's going on there. And so with this, let me thank you very much for your attention.
Well, you very briefly mentioned higher dimensions. So what is the status of work in 2 higher dimensions? Is there any evidence for MBL phases there?
Not much is known. No, there's almost no papers on MBL in higher dimensions. So there's some people believe that MBL will not exist. I will tend to believe that it will exist. Those phase transitions that I'm mentioning, really nothing is known right now. Even in 1D, many of the things I mentioned are controversial, like this nature of those transitions and so on. And there's no numerics, and there's no numerics in, like already numerics in 1D is limited to very small systems, so in 2D you would imagine. But no, people are thinking about it, of course, and there's some papers, but there's very, very few results right now.
And so for the quantum critical glasses, did you look at the Renyi entropies with other parameters, Renyi parameters?
So basically, okay, so let me say this. So like all this structure that we find in excited states for those quantum critical glasses basically mimics what was known for this random cyclet critical points at 0 temperature. And there, if you look at Renyi entropy, so it depends which quantity you average, but there was this paper by Joel Calabrese and Mauricio, I think you were on this, on entanglement spectrum in random singlet systems. So basically, if there are some results from strong disorder RG, and they will basically carry over to those excited states.
So I think then these are not the same as for the quantum critical points, right?
Right, no, okay, but there's some, no, definitely, and you can actually compute them using real space RG, yeah.
So there are states which are certainly not quantum critical, which have log dependence of the entanglement entropy.
Right, so it depends, by here quantum critical I really meant this random singlet type behavior.
Singlet.
Yeah, not CFT of course, yeah, so yeah, sure.
What is this protection of topological inflows?
So just like I said that MBL can protect quantum order, like this Z2 symmetry breaking, you can also protect topological edge. So if you think of just Ising, for example, you would have the Majorana edge modes. And so you can think of MBL protecting those edge modes at finite energy density now. And so there's an interesting question that, so it's not, okay, I said MBL can protect, but it's not clear what kind of edge modes can you actually protect with MBL. And there are some examples of, say, symmetry-protected topological phases where we know that MBL will fail at protecting those edge modes. There are some other examples where we know that MBL would succeed, and the general kind of recipe is not known.
So, how did you check universality?
So, okay, so for this MBL transition in particular, our approach almost assumes that there's something universal to compute, if you want. So I think that's a fair statement. It's a fair statement. We assume that because we take some very effective model that has probably, it's based on the notion, on the hope that there's some universality and that we can simplify the model and maybe there'll be some universal quantities that we can capture.
The model was one.
Sorry? Oh, exponent? Yeah, sure. Oh, there's probably more exponents. There's probably some multifractality going on there, and there's probably many exponents you can define. So universality is more something that, okay, numerically people seem to observe an exponent, and it doesn't depend on models and so on. Our approach essentially assumes universality, and then we observe it if you want. But yeah, if things are completely model dependent, we have no hope to capture it in our simplified model. Right? Yeah.
We need a noise to have this phenomenon.
Yes, you need these other. So people thought about whether you could have many body localization in translation invariant systems. So I'm not an expert on this, but the general consensus is you probably have something that can look like MBL for a very long time, and then you have some crossover scale, and you realize that you're actually not actually MBL. So you can have things that will look very much like this if you have translation invariance. Say if you state two types of particles, one that's very heavy and the other one that's very light, you will have, you'll have some notion, something that will look almost like quench disorder, and you'll see some phenomenon that will look almost like many body. People sometimes call it quasi body localization. But yeah, everything that I told you works only if you have really actual randomness.
Okay.